upon pi cos of alpha. It's clear that as alpha varies, power factor becomes poorer and poorer. As alpha is increased, power factor becomes poorer and poorer. Now, to compare different techniques, we'll have to see what about the reactive power. If the reactive power is reduced to minimum, then we can say the displacement factor has increased automatically. And for that, we'll find out the normalized voltage. Since we have to compare different techniques, that's why instead of taking the absolute value of the output voltage, we'll take the normalized voltage, which is the output voltage upon the maximum output voltage. The output voltage is 2 root 2 upon pi V cos alpha, and the maximum output voltage is 2 root 2 upon pi into V. So it basically becomes cos of alpha. Let us say cos alpha is equal to R. So as alpha changes from 0 to 180 degree, this R changes from 1 to -1. It is a normalized value. Now let us see the reactive power. As far as active power is concerned, we know it is voltage, fundamental current, fundamental power factor. We need this value of I1. And how we have obtained the value of I1 earlier? That V I1 cos of I1, which is power input, is equal to power output. Only the fundamental voltage is responsible for the power flow. That's why power input due to fundamental current is equal to power output. And the input displacement factor is cos alpha. This gets cancelled with this, V gets cancelled with this, and from here I1 is equal to 2 root 2 upon pi I0. Let us make use of this particular current to find out the reactive power, and therefore this reactive power is given by VI1 sin of I1. Fundamental current, sin of fundamental power factor angle. It is V, I1 is 2 root 2 upon pi I0 sin of alpha. Let's find out the normalized value of this, and again it is Q upon what is Q max. Q max will be 2 root 2 V upon 2 root 2 upon pi V I0, so that is sin of alpha. This sin of alpha can be written as 1 minus cos square alpha. Output upon in maximum, that is cos alpha, which is equal to R. Put it here. it becomes 1 minus R square. This is the normalized output voltage. Now if you see the normalized reactive power and the normalized output voltage, you can say normalized voltage square plus normalized reactive power square, that is equal to 1. This square plus this square, that is equal to 1. This is the equation of a circuit. So if we plot normalized voltage versus normalized reactive power, equation of a circuit, this is the maximum output voltage, this is the maximum reactive power. Here alpha is 0, here alpha is 90 degree and here alpha is 180 degree. Only the semicircle is shown because this portion will never be possible. Reactive power will always be drawn from the source. It will never be fed to the source. Current is always lagging in nature, and that's why only the semicircle is shown. This is the locus of fully controlled bridge converter, indicating how the reactive power varies with the output voltage. When the output voltage is maximum, reactive power is 0. As firing angle is increased, output voltage reduces, reactive power increases. Here the average output voltage, which is proportional to cos of alpha, becomes 0, and the reactive power, which is proportional to sine of alpha, becomes unity. And again reactive power becomes 0 and the voltage becomes minus 1. Now, rest of the converters will put on the same graph to see that whether there is an improvement or not. Consider the half controlled bridge converter. Now, in a half controlled bridge converter, if you see the output voltage, it is always positive. It never goes negative. Freewheeling action takes place during that zero voltage period. And if you see the source current, it is positive, 0, negative, like this. It has got its fundamental component lagging this voltage by an angle alpha by 2, that is phi 1, and this is the firing angle alpha. Let's analyze it in the same manner. As far as average output voltage is concerned, it is 2 root 2 upon pi V 1 plus cos alpha by 2. And therefore the normalized output voltage will be 1 plus cos alpha by 2. Divide this by maximum value, which is 2 root 2 V upon pi. Let us say this normalized output voltage 1 plus cos alpha by 2 is equal to R. Cos alpha can be written as 2 cos square alpha by 2 minus 1. Minus 1 gets cancelled with this, 2 gets cancelled with this. It basically becomes cos square alpha by 2. Now, what will be the reactive power? For this we need I1 current, V I1 sine of phi 1. We need this current. And this current we can find out again by equating power input with power output. Simpler way of finding the fundamental current. Power input is Vi1 cos of phi 1. Power output is V0 I0. I1 we want to find out. Cos phi 1 is cos of alpha by 2. This is 2 root 2 upon pi V 1 plus cos alpha by 2 I0. V gets cancelled with this, 2 cancelled with this, 1 plus cos alpha, it is 2 cos square alpha by 2 minus 1, 1 gets cancelled with this, 2 cos square alpha by 2 root 2 upon pi, 1 cos alpha by 2 get cancelled with 1 cos alpha by 2. So I1 becomes basically root 2 upon pi, 2 root 2 upon pi I0 cos alpha by 2. Let's put this I1 here. So it is V 2 root 2 upon pi I0 cos alpha by 2 sin phi 1, that is sin of alpha by 2. If you find out the normalized reactive power divided by 2 root 2 Vi0 upon pi, maximum value, it becomes cos alpha by 2 into sin of alpha by 2. Cos square alpha by 2 is R. So cos alpha by 2 is root of R. This is 1 minus cos square alpha by 2 square root of this. Say root R 1 minus cos square alpha by 2, that is R. Or you can say it is R minus R square. So Qn is square root of R minus R square and VON is R. We can combine these two equations again. If we combine them like this, VON square VON minus 0.5 square plus QN square. So it is VON square plus QN square, then minus 0.25 minus this into 2, so it is VON plus 0.5 square. VON square plus QN square, it is R square and R minus R square, so this gets cancelled, only R is left out. Minus VON, that is R. So this plus this minus this becomes 0, it simply becomes 0.5 square. So it is VON square, VON minus 0.5 square plus QN square, that is equal to 0.5 square. This is also the equation of a circle, but now the center of the circle is this, it is 0.5 x comma y, and the radius of this circle is 0.5. This is a half controlled converter, locus of a half controlled converter. You can see that for the same output voltage, basically the reactive power has gone less. In fact, the maximum value of the reactive power here and here, there is a 50% reduction in the maximum reactive power. It also indicates there is an improvement in power factor, and that's what we have seen right from the beginning. Input displacement factor has become cos alpha by 2 from cos of alpha. So there is an improvement in input displacement factor, and this also indicates there is a reduction in the reactive power, which means there is an improvement in input displacement factor and hence input power factor. But right now we are trying to see the techniques which only improves input displacement factor. These two converters we have discussed right in the beginning. Now see the converters which can be used to improve the power factor further. And all those converters, normalized voltage versus normalized characteristic will be put on the same curve so that we can see how much is the improvement in displacement factor. Now the techniques which are used to improve the input power factor, they can be put in two categories. One, the techniques which basically make use of converters employing line commutation. Whenever you trigger a particular thyristor, it commutates outgoing thyristor. So this is your line commutation. And the techniques in which the converters employing force commutation. Means you can switch them off at any instant. Either you use forced commutation, or you can say make use of self-commutating device. Like MOSFET, IGBT, G2, etc. First, we'll concentrate on this particular converters implying line commutation. Again, there are several techniques which make use of line commutation, but they can be divided into three broad categories. One is use of controlled freewheeling. Second is asymmetrical triggering. Third is sequence and simultaneous control of converters. Controlled freewheeling, use of asymmetrical triggering, or sequence control and simultaneous control of converters. Let's see the first one. What is this controlled freewheeling? Now, to understand this, once again consider fully controlled converter and half controlled converter. Say in fully controlled converter, there is no freewheeling action, and that's why the input displacement factor is cos of alpha. In half controlled converter, there is a freewheeling action automatically, and because of this, the input displacement factor becomes cos alpha by 2. So there is an improvement in input displacement factor, but the problem here is you cannot have negative output voltage. Here you can have both positive and the negative output voltage. So if your requirement is that yes, output voltage can be both positive or negative, you have to go for this. And at the same time, if you want power factor improvement similar to half controlled converter, you have to go for the controlled freewheeling operation. What is done in this? The circuit is identical to your fully controlled converter. Having 4 thyristors, TH1, TH2, TH3 and TH4. Input is V. The load current is assumed to be constant due to high load inductance. Normally, negative half cycle. But in this particular case, when it is a controlled freewheeling, the upper thyristors TH1 and TH2, they are triggered at a firing angle, let us say alpha 1, and the lower thyristors TH3 and TH4, they are triggered at a firing angle alpha 2. The upper half devices and the lower half devices, they have different firing angles, but they are triggered in the same respective half cycles, 1 in the positive, 2 in the negative, 3 in the negative, 4 in the positive. Let us see what will be the output voltage in this case. First, draw the firing pulses of the 4 devices. These are the gating pulses of the 4 devices 1, 2, 3 and 4. Say for example alpha 1 is less than alpha 2. So the firing pulse for thyristor 1 is like this. Although thyristor needs only a short duration pulse, but just to indicate that how long it conducts, a complete 180 degree wide pulse is shown. One will be triggered in the positive half cycle at an angle alpha 1, 2 will be triggered in the negative half cycle at an angle alpha 1. And as I said earlier, this technique is based on line commutated converter. Triggering 2 commutates 1, triggering 1 commutates 2. So 1 and 2 they conduct for 180 degree period like this. What about 3 and 4? 4 will be triggered in the positive half cycle at an angle alpha 2. Alpha 2 is, let us say, somewhere here, which is more than alpha 1. Three will be triggered in the negative half cycle at an angle alpha 2. So the 5 pulses of the 4 devices are like this. Now if you see the output voltage, these are the switching instincts. One and 4, they conduct from this point onwards, and and therefore the output voltage is one and 4. They conduct up to this particular point together. Now at this point 2 is triggered, it commutates 1, 4 continues to conduct, so 2 and 4 they provide a freewheeling path. At this point 3 is triggered, it commutates 4 and therefore 2 and 3 they conduct together. 2 and 3 when they conduct together, output voltage is minus V. Two and 3, so till this particular point they conduct together. And here 1 is triggered, it commutates 2. So now 1 and 3 they conduct together. Another freewheeling path is provided. Output voltage is like this, and if you see the input current, whenever the diagonal devices conduct, current is drawn from the source. When freewheeling action takes place, no current is drawn. When these two devices conduct, a reverse current is drawn. You can notice that as compared to the fully controlled converter, the current is like this. If you want maximum improvement in power factor, and you want to use it as a rectifier, what is done? That alpha 2 is kept 0 and alpha 1 is varied. What will be the resultant voltage? Alpha 2 is 0, so this point is basically shifted here, and therefore freewheeling action starts right from this point. If you want, you can draw the firing pulses once again just to be sure about the conduction of devices.